So last time I skimped out on explaining exactly how I was constructing melody and everything because I wanted to explain it in this video from the ground up. So go ahead and open up Notepad, or better Notepad++ because it's got context. Put in some script tags, call it whatever you want, .html. So first let's make the function that outputs the audio that we give it as input to the speaker. So the first thing that we need is a new audio context, which is a container for running our custom audio. Next, we're going to use the context to create an audio buffer, which is the memory where we store the values for what we're about to play. And the first argument here is the number of channels, since we have left and right stereo channel, that's 2. The length of the buffer is soundArray.length because we're going to put everything we have into the buffer. And then the last thing is the sample rate, which tells us how many samples or values to play each second. The default is 48,000. And then we want to go back over here and we want to save the buffer so we can access the array buffer itself. So we're going to make the left and right channel use the same audio. Which means that we're going to write a for loop here just so that we don't have to duplicate the code. So now we're going to use the array buffer's get channel data function. And this gives us the array for the buffer, which we're putting in samples, so that way we can directly modify the values. So then just simply starting from 0 and going up to the array buffer's length, we set each value of samples equal to each value of our inputted sound array. So it's just copying one array to another. So then we're going to use the audio context to create a buffer source, which is what we need in order to actually play the buffer. And we're just going to set the source's buffer equal to our audio buffer. And then we connect our buffer source to our audio source, and then we play the audio buffer. Let's get rid of this rogue apostrophe, and let's say I is less than array buffer. So that's the play buffer function. Give it an array of values, and it plays it. So we are going to make another change here, though, and browsers these days don't allow you to play audio unless you've interacted with the page somewhat. So that's what we're going to do. We're just going to make a function that only activates once you interact with the page. So for example, clicking. So I'm going to move the context creation code into this other function. And we want to make the context global. So we put it outside the functions. And for now, let's create an empty array as a placeholder and then pass that empty array into our buffer function. And then at the bottom, we say window.onClick equals create audio context, which means that when you click on the window somewhere on the screen, it will do the function. And as a test, let me just drop in the random noise code just to make sure that this is functioning. And it broke because I'm trying to assign the function's return value to window.onClick when I really just want to assign the function to it, so get rid of the parentheses. Alright, good. Let's just get an amplitude and a frequency. Let's just try to play that. So let's just make a sine wave. Let's do I divided by the period that we just calculated, and then we multiply it by 2 pi. And then we can also multiply it by our amplitude so that it will be of the volume that we specified. And that should be a sine wave with a frequency of 440. And let me just verify in Audacity that the sine wave that we just made is exactly the same. Okay, yep, it's the same exact thing. But what other waves can we create? There are generally 3 types of basic waveforms: sine, square, and triangle. These form the building blocks of our synth, along with noise, as well as samples. Though samples are a bit special. Rather than create them, we record a real-life sound, thereby sampling it. This can be of various lengths, but usually something between a split second and a few seconds, which is still a tremendous amount of data, as this can be, tens or hundreds of thousands of individual sample values. You can then go and manipulate that sample to get other sounds, most commonly pitching it up or down. But samples are not the focus of this video, but rather the other waveforms. So all of these waves have the general properties that you might expect, like amplitude, or frequency. But triangle waves have another property, where the peak of the triangle is. It might sound like this normally, but if we move it to the side, we get a sawtooth. But all these waveforms can also be pulsed, meaning the waveform only takes up part of the wave, while the rest is silence. In the case of the square wave, you get other rectangular waves when you do this. And this is what you'd most commonly refer to as a pulse wave. You can also even pulse noise. Lastly, you can change the phase of a wave, moving it left or right, which usually doesn't do much, unless it's in combination with another wave that's in sync with it. And you know what, this tool itself is kind of already a synth. One other thing I want to do is I want to make this context declaration not happen every single time I do this. So if we do that, it'll only create the audio context once. I should probably also change this function name. So different kinds of waves. Well, let's create them. So let's say instead of a sine wave, our wave is a square wave. You can do what, a switch statement here. So we're going to do sine, square, triangle, noise. We can call them what, make sine wave, square wave, triangle wave, noise. And we can shove the sound array into each of them. Right, so let's just make some of those functions now. Okay, yeah, we're going to need the sample rate and the seconds and the amplitude and the period. So we could pass all that information, or I could just do this. From what I understand about coding, the best coding is just making everything global. Okay, now that I've done that, I can just go in here, steal this, put this here. This again to make noise, because we already did that down here. Only difference is that I'm multiplying by 2, but after I do that, I need to multiply it by our amplitude. Now, how do we do square wave? Oh, you know what? We need an argument for each of these. What am I thinking? Right, well, okay. So a square wave is always basically going to be 1 or -1. So I guess we want to modulate it by the period. Do we have that? What's the period? Sample rate. Yeah. So I guess, I guess we'd say whatever we're on, we want to modulate that by the period. So then we'd get our I that's somewhere in between 0 and the period. We want half of that to be 1 and then half of that to be -1. We can divide it by half of the period so that it will be 0 point something when it's below half of the period's length and 1 point something when it's above that. And then we can go and parse in that to cut off the decimal places, and it'll just be 0 or 1. This is kind of exactly like the noise. We have something that's between 0 and 1, so we can just multiply by 2 and then go and subtract 1. and we multiply it by the amplitude. Let's see if that works. Okay, that sounds like a square wave. Alright, and now last is triangle, which I think is the most complicated. Let's say that this is our triangle wave, right? And so there's kind of three regions of this, right? So this is one going up, this is another going down, and this is another going up again. And you could model this in an even simpler way, but I think it becomes easier to do it this way when you start involving pulses. And basically what we're going to do is we're just going to make an if statement for each of these three scenarios. And now there are two special points on the triangle wave. One is right here. This is our tri-peak value, as I'm going to call it. So within half of this wavelength, tri-peak would be in the center, so we would say its value is 0.5. Meanwhile, if it was a sawtooth like this would be our tri-peak, and this would be at 0. If it went the other way, like this, then tri-peak would be 1. Basically, we're going to divide that value by 2, and that gives it a percentage of how far it is through the entire wave. And this value right here is 1 minus tri-peak over 2. And so we're going to use those as our if statement comparisons to try and figure out how this wave is working. You know what, I'm going to declare tri-peak outside, and I'm going to make it 0.5. And then let's just make some variables here so that way it's easier to refer to things. So tri-peak divided by 2, I'll call TP2, and that's tri-peak divided by 2. And then ITP2 is kind of like the inverse of tri-peak over 2, 1 minus it. So we just do 1 minus TP2. So like before, we're probably going to want to modulate it by the period first, and then divide by the period, so that way we have the percentage that I is through the period. And I guess I'll just call that perc for percentage. And now let's create our regions. So if perc is less than TP2, else if perc is less than ITP2, else it's in the last region. And the value that we're adding to the sound array is our sample, so I'm just going to call it samp and initialize it to 0. I don't know, what perc divided by TP2 is our samp, right? Also, yeah, at the end of this, right, we could say sound array equals samp, right, but multiplied by our amplitude. So the first part is from 0 to the top of the wave. Now this is from the top to the bottom of the wave. So how do we do that? So first off, we want to subtract the progress off, you know, in terms of percentage-wise that we already made. So we're going to subtract TP2. And then we want to, I think, just divide that by ITP2 minus TP2. And that gives us our percentage through the downward slope. But remember, since we're going from the top of the wave to the bottom of the wave, right, we're going from 1 to -1. So we have to make it so 0 goes to 1 and 1 goes to -1. So how do we do that? Multiply by -2 and add 1. Does that work? Subper multiplied by -2 plus 1. And the last case is much like the first case. We want to subtract off most of our progress to the wave to that point. And then we just divide by TP2. We're going from -1 to +1. We just subtract 1 from this entire thing. So let's make sure the frequency is correct by doing the same thing in Audacity. Sounds like that. Sounds exactly the same. So we did it correctly. Alright, so now let's try and play specific notes. The problem is frequency is not really that useful because most people don't know the frequencies of each and every note. So I guess within init audio context, we could probably do init keys as well. Then maybe I feel like it might be more accurate to say init sound. There are 88 keys on a piano. Our reference pitch is middle A or whatever, the concert A. I don't really know. Whatever. It's just 440. Okay. What number on the piano is that? So 0, 1, 2, 3, 4, 45, 46, 47, 48. So our reference index is in fact 48. While I is less than num notes, I++. What was the formula of this again? Where are those slides? Where'd I put them? the 12th root of 2 raised to the note we're trying to get to. Alright, that's not too bad. I say 440, but I'm using the reference pitch specifically. I'm multiplying that by 2 to the 12th. I'm going to make that a variable. Some people would argue that I should be making this a constant because it's not like 2 to the 1/12 is ever going to change. But if you wanted to create different scales, you could just edit this 2 to 1/12 value. Okay, wait, what was I doing? Reference pitch multiplied by 2 to the 1/12 raised to whatever note we're trying to get to. So I is the note that we're trying to get to, but you can't just say I because you have to compare it to the reference pitch. So I think you'd say I minus ref IDX. We need to save this into something. Why not just call it notes and save that as an array of all our notes, and we can just say notes I is equal to reference pitch. So if we wanted to play a specific note, we would just have to know the index. And let's try playing an A. Ooh, it's like almost music. Wow, what a song. Let's just try and maybe make a function that appends notes to the sound array rather than just doing one at a time. So I'll call that function append notes. Append note, and that would be, we'd give it a frequency as well as a note length. And let's drag this over to here. And yeah, actually this period declaration then should probably go into each of them. So instead of multiplying by seconds, we multiply by note length. Just do sound array dot push. So I guess let's create a melody. So here's the melody I was using for Megalovania. We could say something like for var I is equal to 0 while I is less than melody dot length, and then say append notes melody I, and then some kind of note length. We probably need to say if the frequency is equal to -1 and don't do anything. Yeah, I guess we'd have to have a make silence as well, right? We just push 0 onto the array. Let me just drop this in here because these are the key indices of each of the notes, and let's see what happens. Type is not defined. All right, well, I mean, I'll figure out a better place to put this later. Okay, I think something went wrong. I threw in the melody ID. That's the key index. We need to get that from notes, so we need to say notes of the melody, right? Right, okay, that's happening because multiple notes aren't continuous. I have a hard time caring that much about that, though. Make silence and then return, right? Because otherwise, wait a minute, what is happening? Oh, hold on, I'm screwing this up. Do melody I, then notes I. Why doesn't it sound totally broken? I shouldn't call this freak. I should call this key IDX and say that the frequency is equal to the key IDX. Ask is the key IDX -1. Okay, that will make it sound a little better, I think. Yeah, alright. Now I can actually hear the rhythm and the noise. I'm done with frickin' sound array. Alright, I'm sorry. I just, this is getting so annoying. Sound array, you're going global. Sorry, it's just like there's so much less passing that has to be done. Yeah, I don't need it here either. Instead of saying var sound array, just say sound array. And let's just put this up here. Okay, so now here I was saying sound array.push, but instead of doing that directly, I'm going to have a append sample. Append sample takes in a value, and then we'd say sound array.push of the value. But we want to apply attack, decay, sustain, release to this value. So, you know what, I should probably go and cover exactly how attack, decay, sustain, release works, shouldn't I? And you know, I was going to draw my own thing and explain it here, but oh my god, Wikipedia is just it's way better at this. Basically, when you press a note on a keyboard, the note isn't immediately supposed to be loud. There's a time period called the attack in which it increases to its maximum velocity. So we can specify that. That's a time period for attack. And then after that, it doesn't stay at full volume. It actually decays a bit until it gets to the sustain amplitude. And so that second time period here is called the decay. And then over here we have sustain. Sustain is different than the others because it's an amplitude. And for as long as the note is going on for, it'll stay at the sustain amplitude. And then finally, when you release the key or you release the note, we slowly bring it back to 0 so you can't hear it anymore, right? But it doesn't just immediately stop the note, it slowly fades out, right? And the time it takes to slowly fade out is the release time. So what we're going to do for attack, decay, sustain, release is we're just going to specify all of these values. And we're also going to do it instead of in seconds or anything like that, we're going to do it in percentage. So if you were to add up the regions of attack, decay, sustain, release, they should all add up to 1 because that's 100% of what the note's value is. So maybe 0.1 for attack, 0.2 for decay. Sustain is different. I guess we'll say it's half of the volume. And then lastly, release, give it a quarter second for that. So actually, yeah, in order to do ADSR, what we're going to need to know is we're going to have to know what percentage we are through the note here. So that would be I divided by sample rate times note length. We'll say I divided by SXN is our through note. And we'll pass this in over here. So now we know the percentage of the value that's through the note. So now we can just do some if statements here. So if through note is less than attack, then that means we're in the attack phase. If through note is less than decay, then that means that we are in the decay phase. If through note is greater than release, then that means that we are in the release phase. Otherwise, we're in the sustain phase. For sustain, we just say sustain multiplied by our value, and we can return that. Okay, and then for attack, this is a little bit more difficult. Through note divided by attack. That's our through attack, so that's our percentage of the way through the attack. So now we just say value times equals through attack. For decay, we have to do a little bit more because we have to know the percentage through the decay, and that's a little bit more difficult, but not really. We have to say decay minus attack because that's the interval of how long the decay takes. And then we also have to say through note minus attack as well, and that will give us our through decay. Yep, okay, we have to say 1 minus through decay. We're going from full amp to sustain. So we need to add the sustain value because it should never go below sustain. And then I think we need to multiply it by 1 minus sustain. One more step in here. We need to make a sus value, right? And that's sustain multiplied by value. So yeah, sus value, and then 1 minus sus value, right? I think we want value minus sus value. Yeah, all right, there we go. And lastly, we have the release. All right, so we're going to take our through note, and we're going to subtract off 1 minus release. And that will give us how far along we are in the release. And then we have to divide by release itself, and then that gives us our percentage. So that is our through release. And we have to go down from sustain down to 0. So let's get our sus value again. And our sus value is sustain times value. We want it to go from 1 down to 0. So we'd say 1 minus through release. And we multiply this by sus value, right? And I think that's right. So that's our attack, sustain, decay, release. So let's see if that actually functioned. Unexpected number equals. That doesn't sound any different. Let's have longer notes so that way we can see if we can hear it. Okay, that's definitely not doing it. So hold on, what are we using right now? We're using square wave. So I feel like I need to actually go and debug this. Okay, so value equals ADSR of value. So let's jump into that function. Through note is undefined. Oh, okay, I see the problem. I only gave it value. Yeah, okay, let's make sure that we are taking in through note, and then also that we're sending through note into our ADSR. That doesn't sound right. That sounds like it's doing the same thing twice. Alright, what would I be doing wrong? You know what? I think the easiest thing to do is just get the actual values so I can see what's happening. Yeah, before we play the buffer, let's just check what sound array is. Okay, so we see it slowly increasing in amplitude. Okay, yeah, so it goes all the way up to 0.5, 0.25. It should stop at 0.25 and it should stay there for a while, which is what it's doing. Okay, yeah, so here's the problem. We jump straight from 0.25 down to 0.75, so that's wrong. I see the problem. I said release is 0.25, which is correct, but I need to say 1 minus release here. Alright, now that actually sounds like an actual attack, decay, sustain, release envelope. You know what, I'm gonna make another variable in here called ADSR on. That way you can see the difference easier. If ADSR on, then we do the attack, decay, sustain, release. Okay, and so let's compare that to what it sounds like when this is false. So it's louder at the beginning and you can clearly hear that. I mean, it's hard to tell the exact difference here, but it would make a difference in lots of other cases, I think, probably. This kind of way of doing melody programming isn't very user-friendly, so perhaps next time we can go and try and make some kind of user interface to improve on this. And then maybe we'll get to like channels and additive synthesis or whatever.